The Dawn of Self-Propulsion, a Dream Takes Hold. Good morning, everyone, and welcome to Wheeled Wonders, the show that explores the incredible journey of the motor vehicle. Today, we're going to dive deep into the fascinating history of how we went from horse-drawn carriages to the sleek, powerful machines that dominate our roads. But before we get to the roar of the engine, let's cast our minds back to a time when the idea of a self-propelled vehicle was little more than a whisper in the minds of dreamers and tinkerers. For centuries, humanity had relied on animal power, wind, and water to move people and goods. The very concept of a machine that could move itself without external force was revolutionary, almost fantastical. Early thinkers, inspired by the intricate mechanisms of clocks and the potential of steam power, began to imagine a world where travel was faster, more efficient, and less dependent on the whims of nature. These were the seeds of innovation, planted in an era of burgeoning scientific inquiry and mechanical experimentation. The 17th century saw figures like Ferdinand Verbiest, a Jesuit missionary in China, construct a small, steam-powered cart, essentially a toy, which is often cited as one of the earliest examples of a self-propelled vehicle. While not intended for passenger transport, it showcased the fundamental principle. This wasn't just about a practical application, it was about the intellectual leap, the audacious thought that machinery could mimic the power of muscle. The scientific understanding of thermodynamics was still in its infancy, yet these early pioneers were already grappling with the conversion of heat into mechanical energy. The desire to conquer distance and connect communities was a powerful driving force, fueling the imaginations of engineers and inventors across Europe. The Industrial Revolution, though still some time away from its full fury, was already stirring, creating an environment ripe for such transformative ideas. The stage was set, not for a single inventor, but for a collective human endeavor to redefine transportation. The spark of invention, a name etched in history. While many contributed to the early concepts of self-propelled vehicles, one name stands out as the widely recognized father of the modern automobile, Karl Benz. In 1886, Benz unveiled his Benz patent motorwagen, a three-wheeled vehicle powered by a single-cylinder, four-stroke gasoline engine. This wasn't just another experimental contraption, it was a commercially viable design, albeit a very early one. Benz's genius lay not just in the engine itself, but in integrating all the necessary components, the chassis, steering, and transmission, into a cohesive, functional unit. He understood the need for a lightweight yet sturdy frame, a reliable power source, and a mechanism to control its direction. His engine, operating on the internal combustion principle, was a marvel of its time. The controlled explosion of gasoline vapors within a confined cylinder, driving a piston, was a revolutionary concept that harnessed chemical energy to produce kinetic energy with unprecedented efficiency for personal transport. The thermodynamic cycle he employed, now known as the Otto cycle, though refined by others, was a significant scientific advancement. The spark plug, a critical component for igniting the fuel-air mixture, was also a product of this era, though its complete refinement came later. Benz's innovation was a testament to meticulous engineering and an unwavering belief in his vision. He faced skepticism, financial challenges, and the inherent difficulties of working with new and untested technologies. Imagine the sheer audacity of trying to convince a world accustomed to horses that a noisy, smoky machine was the future. But Benz persevered, driven by a passion for invention and a deep understanding of mechanical principles. His wife, Bertha Benz, also played a crucial, often unsung role, not only financially supporting his endeavors, but also undertaking the world's first long-distance road trip in the patent motorwagen in 1888, proving its practicality and reliability. This journey, a marketing masterstroke, brought the automobile to public attention and began to dispel fears about its viability. The race for power, early competitors and innovations. While Karl Benz had a significant head start, he was by no means alone in the quest to develop the automobile. Across Europe and eventually in America, brilliant minds were grappling with similar challenges, each striving to improve upon existing designs and introduce their own innovations. Gottlieb Daimler and Wilhelm Maybach, for instance, were simultaneously developing their own high-speed internal combustion engines, focusing on four-wheeled vehicles. Their 1886 Daimler motorized carriage ran on petroleum and demonstrated a different approach to vehicle design, emphasizing speed and elegance. The competition was fierce, fueled by the potential for immense commercial success. Each inventor brought unique scientific insights to the table. Some focused on improving fuel efficiency, exploring different fuel types beyond gasoline. Others concentrated on ignition systems, moving from unreliable hot tube ignitions to more practical electrical spark ignitions. The metallurgy of engine components was also undergoing rapid advancement, with engineers experimenting with new alloys to create lighter, stronger pistons, crankshafts, and connecting rods that could withstand the intense pressures and temperatures within the combustion chamber. The development of more efficient cooling systems, from basic water tanks to rudimentary radiators, became crucial as engine power increased. Without effective heat dissipation, engines would quickly overheat and fail, a direct application of the laws of thermodynamics. Gearboxes, initially very simple, began to evolve, offering multiple ratios to better manage engine power and speed across varying terrains. Steering mechanisms, from tillers to rudimentary steering wheels, were also being refined for better control and maneuverability. The early automotive landscape was a hotbed of experimentation, a testament to the scientific method in action. Each failure led to new learning. Each success paved the way for further refinement. The pursuit of the perfect engine and the ideal vehicle was a relentless, collaborative, and often competitive process, laying the groundwork for the industry we know today. The American Revolution, Ford and the assembly line across the Atlantic, America was about to usher in a new era of automotive production, one that would truly democratize the motor car. While European innovators focused on craftsmanship and luxury, Henry Ford had a different vision, an affordable, reliable car for the masses. His genius lay not just in designing a vehicle, the iconic Model T, but in revolutionizing the way cars were built. The year 1913 marked a pivotal moment with the introduction of the moving assembly line at Ford's Highland Park plant. This wasn't merely an organizational change, it was a scientific application of efficiency and industrial engineering principles. By breaking down complex tasks into smaller, repetitive steps and bringing the work to the worker, Ford dramatically reduced production time and cost. Before the assembly line, building a single car could take over 12 hours. With the assembly line, it was reduced to a mere 93 minutes. This was a triumph of process optimization, leveraging principles of motion study and time management. The standardization of parts, a concept pioneered by Eli Whitney for firearms, was taken to a new level in the automotive industry. Precision machining became paramount to ensure interchangeable components, reducing manufacturing defects and simplifying repairs. This scientific approach to production meant that cars were no longer bespoke creations for the wealthy, but mass-produced commodities accessible to a much broader segment of society. The Model T itself was a masterpiece of simplicity and ruggedness, designed for the rough American roads of the early 20th century. Its planetary gear transmission, robust chassis, and reliable four-cylinder engine made it a workhorse. Ford's commitment to vertical integration, owning everything from the rubber plantations to the steel mills, further streamlined his operations and controlled costs, showcasing a mastery of supply chain management long before the term was coined. The impact of the assembly line extended far beyond the automotive industry, becoming a foundational principle of modern manufacturing across the globe. Engines of change, from V-twin to V8. As the automobile gained traction, the relentless pursuit of more power and greater efficiency continued, driving significant advancements in engine design. Early engines were often single or two-cylinder affairs, but soon engineers began to explore multi-cylinder configurations to smooth out power delivery and increase displacement. The V-twin engine, with its cylinders arranged in a V shape, became popular in motorcycles and some early cars for its compact design. However, for serious automotive power, more cylinders were needed. The inline-4 and inline-6 configurations became standard for many years, offering a good balance of power, smoothness, and complexity. The scientific understanding of combustion dynamics, valve timing, and crankshaft balancing became increasingly sophisticated. Engineers meticulously studied the fluid dynamics of air and fuel mixtures entering the cylinders, optimizing intake and exhaust manifold designs for better volumetric efficiency. The development of overhead valve, OHV, and later overhead camshaft, OHC, designs allowed for more precise control over valve actuation, leading to higher engine speeds and better breathing. But perhaps the most iconic development was the V8 engine. First introduced in Cadillac in 1914 and popularized by Ford in the 1930s with its flathead V8, this configuration offered a potent combination of power, smoothness, and a distinctive rumble. The V8's 8 cylinders, arranged in 2 banks of 4, provided a continuous power stroke, resulting in incredibly smooth operation. The challenges lay in balancing the crankshaft to handle the forces from all 8 pistons and in designing an efficient cooling system for such a powerful engine. The materials science behind engine block and cylinder head casting also advanced significantly, allowing for lighter yet stronger components capable of withstanding the immense pressures of modern combustion. The journey from the rudimentary single-cylinder engine to the complex, powerful V8 was a testament to continuous engineering innovation, driven by the desire for speed, performance, and a more refined driving experience. Aerodynamics and aesthetics. The shape of speed. Beyond the engine, the exterior of the automobile underwent a dramatic transformation, driven by both aesthetic desires and the growing understanding of aerodynamics. Early cars were essentially carriages without horses, boxy and upright, offering little resistance to the wind. As speeds increased, however, the detrimental effects of air resistance, or drag, became apparent. Engineers and designers began to recognize the scientific principles of fluid dynamics, understanding that a more streamlined shape would reduce drag, improve fuel efficiency, and enhance stability at higher speeds. This led to the gradual evolution of automotive styling, moving from purely functional forms to more sculpted, flowing designs. The 1930s saw the emergence of streamlining as a dominant design philosophy, inspired by trains, aircraft, and even fish. Designers like Norman Bell Geddes and Raymond Loewy popularized the teardrop shape and smooth, rounded contours. The concept of the coefficient of drag, CD, became a crucial metric in automotive design, and wind tunnels, once solely the domain of aircraft engineers, became essential tools for testing and refining vehicle shapes. Materials science also played a role. The transition from heavy, rigid wooden frames and steel panels to lighter, more malleable steel stampings allowed for more complex and aerodynamic bodywork. The development of safety glass and eventually curved windshields not only improved visibility, but also contributed to the overall aerodynamic profile. The interplay between form and function became increasingly sophisticated. While aesthetics drove consumer desire, scientific principles dictated efficiency and performance. The goal was to create a vehicle that not only looked fast, but was also engineered to cut through the air with minimal resistance, a perfect blend of art and science. This chapter marks the shift from simply making a car move to making it move gracefully and efficiently. Safety first, from seatbelts to crumple zones. As cars became faster and more numerous, the issue of safety moved to the forefront, transforming automotive engineering into a field deeply intertwined with biomechanics and material science. Early vehicles offered little protection in the event of a collision, leading to severe injuries. The scientific study of impact forces and human tolerance became paramount. The invention of the three-point seatbelt by Volvo engineer Niels Bohlin in 1959 was a monumental breakthrough. This simple device, a marvel of biomechanical engineering, distributes impact forces across the strongest parts of the human body, significantly reducing the risk of fatal injuries. Its widespread adoption, often mandated by law, saved countless lives and remains a cornerstone of passive safety. But safety went far beyond restraints. The concept of crumple zones emerged from the understanding that energy from an impact could be absorbed and dissipated by strategically designed areas of the car's structure, protecting the rigid safety cell around the occupants. This involved meticulous finite element analysis and crash testing, simulating real-world collisions to understand material deformation and energy transfer. The use of high-strength steel alloys in critical areas and carefully engineered crush zones became standard practice. Airbags, first conceived in the 1950s but refined and widely adopted in the 1980s, provided an additional layer of protection by rapidly deploying a cushion of air to mitigate impact with the dashboard or steering wheel. The chemical reactions that rapidly inflate airbags, typically involving sodium azide, are a fascinating example of applied chemistry in safety engineering. Anti-lock braking systems, ABS, traction control, and electronic stability control, ESC, are active safety systems that use complex algorithms and sensors to prevent accidents in the first place, applying principles of physics and control theory to maintain vehicle stability. The evolution of automotive safety is a continuous process, driven by rigorous scientific research, advanced materials, and sophisticated engineering, demonstrating a profound commitment to protecting human life on the road. The digital revolution, computers, and connectivity. The 21st century has brought an unprecedented integration of computer technology into the automobile, transforming it from a purely mechanical device into a sophisticated, rolling supercomputer. The digital revolution has impacted every aspect of vehicle operation, from engine management to entertainment. Modern engines are controlled by complex engine control units, ECUs, that constantly monitor dozens of parameters: fuel injection timing, ignition timing, airflow, exhaust gas composition, and make real-time adjustments to optimize performance, fuel efficiency, and emissions. This involves sophisticated algorithms and high-speed data processing, applying principles of cybernetics and control engineering. The transition from carbureted engines to electronic fuel injection was a monumental leap, offering unparalleled precision in fuel delivery and combustion. In-car entertainment systems have evolved from simple radios to multimedia hubs with touchscreens, satellite navigation, and seamless smartphone integration, powered by embedded processors and high-speed data buses. Connectivity is another major frontier. Cars are now equipped with telematics systems that can communicate with emergency services in the event of a crash, provide real-time traffic updates, and even allow for remote diagnostics and software updates. The Internet of Things, IoT, is extending to vehicles, enabling vehicle-to-vehicle, V2V, and vehicle-to-infrastructure, V2I, communication, which holds immense promise for improving traffic flow and preventing accidents. Sensors, from radar and LiDAR to ultrasonic and camera systems, form the backbone of advanced driver assistance systems, ADAS, providing features like adaptive cruise control, lane keeping assist, and automatic emergency braking. These systems rely on complex sensor fusion algorithms to interpret their surroundings and make intelligent decisions, mimicking aspects of human perception and decision-making. The car has become a mobile data center, continuously collecting, processing, and acting upon vast amounts of information, fundamentally redefining the driving experience. The electric renaissance, a sustainable future. After a century dominated by the internal combustion engine, the automotive world is now undergoing a profound shift towards electrification, driven by environmental concerns and advancements in battery technology. While electric vehicles, EVs, have a surprisingly long history, dating back to the late 19th century, they were largely eclipsed by gasoline cars due to limitations in battery range and charging infrastructure. Today, however, those limitations are rapidly being overcome. The scientific breakthroughs in lithium-ion battery technology have been a game-changer, dramatically increasing energy density and reducing costs. These batteries operate on complex electrochemical principles, storing and releasing energy through the movement of lithium ions between electrodes. Engineers are continuously optimizing cell chemistry, thermal management systems to prevent overheating, and battery pack design to maximize range and lifespan. Electric motors, offering instantaneous torque and high efficiency, have replaced traditional internal combustion engines, eliminating tailpipe emissions and significantly reducing noise pollution. The efficiency of converting electrical energy into mechanical energy in modern EVs is remarkably high, often exceeding 90%, far surpassing the thermal efficiency of even the best gasoline engines. Regenerative braking, a clever application of physics, allows EVs to recover kinetic energy during deceleration and feed it back into the battery, further extending range. The development of widespread charging infrastructure, from fast chargers to home charging solutions, is crucial for widespread EV adoption. Smart charging systems are being developed that can manage grid load and integrate with renewable energy sources. This shift is not merely an engineering challenge, it's a societal one, requiring changes in infrastructure, energy production, and consumer habits. The electric renaissance represents a sustainable future for personal transportation, addressing critical issues of climate change and air quality, and pushing the boundaries of what is possible with clean energy. The road ahead, autonomous and beyond. Where are we headed next? The future of the motor vehicle promises to be even more transformative, with autonomous driving and novel transportation solutions on the horizon. Self-driving cars, once the stuff of science fiction, are rapidly becoming a reality, thanks to breakthroughs in artificial intelligence, machine learning, and sensor technology. These vehicles rely on an array of sophisticated sensors, LiDAR, radar, cameras, ultrasonic, to create a real-time, 360-degree understanding of their surroundings. The data from these sensors is then processed by powerful onboard computers running complex algorithms that interpret the environment, predict the behavior of other road users, and make split-second decisions. This involves advanced computer vision, deep learning networks, and probabilistic reasoning, mimicking and often exceeding human perception and reaction times. The challenge lies not just in technical execution, but also in ethical considerations, regulatory frameworks, and public acceptance. Beyond full autonomy, we're seeing the emergence of entirely new modes of personal transportation. Urban air mobility, with electric vertical takeoff and landing, eVTOL aircraft, promises to revolutionize intra-city travel, bypassing congested roads. High-speed rail and hyperloop systems aim to connect distant cities with unprecedented speed and efficiency. The concept of mobility as a service is also gaining traction, where car ownership may become less common, replaced by on-demand, shared, and interconnected transportation networks. The materials used in future vehicles will be even lighter, stronger, and more sustainable, with advancements in composites, smart materials, and even self-healing coatings. The energy sources may diversify further, exploring hydrogen fuel cells and other renewable power generation methods. The journey of the motor vehicle, from its humble beginnings as a noisy experimental machine to its current status as a sophisticated, connected, and increasingly autonomous system, is a testament to humanity's relentless drive for innovation. The road ahead is undoubtedly filled with challenges, but also with incredible possibilities, promising a future of mobility that is safer, more efficient, and more sustainable than ever before.